Good afternoon, class. Today we'll be looking at the molecular orbital theory. What the essence of in studying this particular course? The main object here is that we use molecular orbital theory to determine whether a molecule is stable or not stable, and also to know whether a molecule is paramagnetic in nature or diamagnetic in nature. So there are some tests in chemistry that you just come across. They will tell us whether this molecule is exist or not exist. That is, whether a molecule is stable or not stable. So it is molecular orbital theory that will let you know whether a molecule is stable or is not stable. And it can be classified in two ways. We have molecular theory or homonuclear theory, or heteromolecular theory or heteronuclear molecular orbital theory. So today we'll be looking at the homonuclear first. Now, in homomolecular orbital theory, look at how the word sound. Homo. The word homo means same thing or the same kind. That is, homonuclear means when the same kind of atom are combined together to form a molecule, then we call that such molecule homonuclear molecule or homomolecular. Now, let's begin with the first example in this context. Let me look at hydrogen molecule. You know, when you have one hydrogen, we refer to it as what? As elements. But by the time you now combine two hydrogens together, then you're going to have just one hydrogen molecule called hydrogen gas, which is H2. This H2 is a molecule. Now, how will you know whether this molecule is stable or not stable? In that aspect, you need to split the molecule into two. You take it out and you share the molecule into two. That is, you split the elements. After that, then you write the electronic configuration for it. You know that hydrogen is number 1. That should be what? 1x1 for the first one, and the second one will be 1x1 as well. In that, then you will now go and draw the molecular orbital diagram for the hydrogen molecule. Now, if you want to do that, it's very simple. This is how to draw it. But before you are going to do that, you have to show an arrow to indicate the energy level of the diagram. In case if you are dealing with written, you should don't forget this in chemistry, and you are going to write increasing energy level. Just say increasing energy level. So you can just put little line to indicate that that thing is always go up. In that, then you start to draw the diagram like this. It's very simple. Just make the diagram out. Then you join it here. Just make a dotted line here. Now, in this diagram, there are two things involved here. We have bonding orbital and anti-bonding orbital. Let me quickly explain that. This place that you're looking at here, we call it bonding orbital. On top of bonding orbital, you have what we call anti-bonding orbital. So anti-bonding orbital is like the opposite of the bonding orbital. It is very simple. Now, the electrons of the molecule, the two hydrogen atoms, then you share them at each side of this diagram. You put one electron here, the one of first hydrogen, and you put the second one of the electron at this side. Then you now come to share the electron inside the orbital. Keep it in mind, an orbital has ability to take just what? One and two electrons at a go. Then you have to fill the bonding orbital before you move to what? To anti-bonding. So, but how can you say the difference between bonding orbital and anti-bonding? This is 1s, and s is in sigma bonding. If you really remember the chemistry of 100 level days, then that should be 1 sigma x. You come to the antibonding by saying 1 sigma x, then you put asterisk to indicate the what? Antibonding. 1 sigma s bonding orbital, 1 sigma x star antibonding. That is the meaning. So now, if you want to share electron in this bonding and bonding orbital, we always consider the bonding orbital filled before you move to the what? To antibonding. That was the key on how to fill the electrons in bonding orbital. Then the electron of this one will come here, and the second one of this will come to this side as well. So you have already fulfilled. This orbital has been filled. Now, no more electron again. Definitely, we are not going to give anything into what? Into anti-bonding, because the two electrons that we have, you can see, has been filled the bonding orbital. So this is for hydrogen molecule. So now the question is this molecule exist or not? That is it stable or not stable? If you want to know whether a molecule is stable or not stable, you have to calculate what we call bond order. Bond order has a formula which is very simple to know. Bond order is equal to total electrons in bonding orbital minus the one of anti-bonding, total electron of anti-bonding orbital, divide by 2. That is the total electron that you have in bonding orbital, which is 2. See, 2 minus, go to anti-bonding, you have nothing in anti-bonding here, you say 0, divide by 2. Then it's equal to 2 minus 0, that is 2. 2 divided by 2, then you are going to have 1. It means that this molecule, it exists. That is, the molecule is stable. Whenever you calculate your bond order and you get either a fraction or you resort to a particular number, be it a rational or irrational number, you have to know that that particular molecule is stable in chemistry. But if you get 0, it means that that molecule is unstable. So hydrogen molecule is stable with just single bond. That is why we have 1 as our bond order. Now, this molecule is it paramagnetic or diamagnetic in nature? This molecule is diamagnetic in nature. If you want to know whether a molecule is diamagnetic or paramagnetic, go to the orbital. Anywhere you say that electron is single, it is not paired. That is, there's no 2 electrons. That particular molecule is para at that particular place. But if you look at this one now, it is paired. You have 2 electrons here. It means that orbital is paired, and then the electron is paired in that orbital. Then you have to know that this molecule is what is diamagnetic in nature. So let me continue with other elements. So after hydrogen, we have helium. So let me look at helium molecule. So this is helium molecule. You split it into 2, helium 1 and the second helium. Then you write the electron configuration of it. That is 1s2 and 1s2. The next thing is that you draw the arrow. You indicate whenever you're supposed to indicate increasing energy level. Then you draw the orbital diagram for that. It is very simple. I use the first one to explain that. Then you move on to draw the diagram. Then so now after that, you bring the 2 electrons of each helium to these sides. So now after that, then you share it inside the orbital. Now before you go, indicate the bonding orbital and antibonding. This should be 1 sigma x, and this should be what? 1 sigma x antibonding. You can see 1x. So and it's bond, the bond here is antibonding. Now is sigma bond, so not pi. And you get to pi bond, I will explain that. Now let's go. This is how to draw the diagram of helium. After you draw the diagram, then you have to share the electrons in bonding and antibonding. So 1 electron will come to this side, and 1 from here also. You pair them. Remaining one electron from each side. So you also take 1 to this side and 1 to the side. So the 4 electrons, 2 here, 2 here, it has been shared inside the orbitals now, if you can see. Now calculate the bond order, whether the molecule is exists or not. So you need the bond order. Total electron in bonding orbital, which is 2, minus the one of antibonding, which is 2 as well, divide by 2. That should be 0 divided by 2. Our answer is what? Our answer is 0. It means that this particular element is not stable. This molecule is not stable in chemistry. The molecule is not stable. That's the meaning of this. Then let's check whether the molecule is paramagnetic or diamagnetic. As you're looking at it, it's very simple. You can see the electrons are paired in the orbital. It is diamagnetic in nature. It is not what? It is not paramagnetic. Now let's move on to see the next one. Now let's see the molecule of lithium. This is lithium, the molecule of lithium. Then you split the molecule of lithium into 2 by saying Li. The second one, Li. Now, write the electron configuration for helium. That should be 1s2, 2x1, because lithium is number 3. If you want to know this, go and check some videos that I've already uploaded. You will see how to write the electron configuration. It's very simple. Then you write this one to 1s2, 2x1. So in this place, you see that thing has increased from 1s to 2x. Then our diagram now is now 2. After you draw the first one, which is 1s, you draw the next one for 2x. So then you first draw your arrow first. You indicate it, increasing energy level. So you first draw the one of 1s down by saying so this is for 1 sigma x, 1 sigma x antibonding. So this one is for 1x. So you draw the next one like this as well for 2x. You just indicate it as 2s. So it's very simple. So you call this one 2 sigma x, and this one will be 2 sigma x antibonding. That's just differences. Now, the one of 1x, you put the 2 electron. You know, they have two electron. The first one, second one. The second 1x. Then 2s, they have just one electron on each. So 1 electron will be here, and the second electron also will be here. Now, you want to share the electrons in the orbital now. In this place, you know, one will come from this, one will come from this. This one will be filled first. Then you consider the antibonding of this one. One of these will come and one of these will come. So I've already filled this one. Then you move to the 2x. So this is one here, one here. You fill the bonding orbital below before you consider the one of antibonding above. So there's no more electron again to consider the antibonding in 2s. Though now you want to know whether this molecules exist, then you calculate the bond order by saying is equal to. Now you can do this one in 2 ways. You can say total electron that you have in bonding orbital. Don't forget you have 2 in bonding orbital here. Go to 2s also, you have 2 in bond orbital. So total electron in bond orbital now is now 4. So you say 4 minus. Now here you have 2 electron in antibonding. Here you have 0 electron in antibonding. That is 2. So that should be 4 minus 2 divided by 2, and you have 2 divided by 2, and that should be what? And that should be 1. You see, it means that this molecule, it exists. You can also calculate it in another way by saying, or you can only use this one to calculate your bond order by saying 2 electron in bonding orbital minus 1 of antibonding, which is 0. Say 0 divided by 2, and that should be 2 divided by 2, and you are going to have 1 as your answer. So the two method is correct. You get, because this one is like the one of helium, so it has cancelled each other because I'm going to get 0. So you can now use one to determine your bond orbital. So either this method or this method, the 2 is correct in calculate the bond order. So now let's check whether the molecule is paramagnetic in nature or diamagnetic. So you can see all the electrons are well paired. So there's nothing like single electron. So it is diamagnetic in nature. Thank you for watching. Subscribe to our channel. Give us comments and help us to share our videos. May God bless you. Thank you.